Now the partial of r with respect to v. So this time sine of u is like a constant. That derivative is going to go to 0. So what do we get here? Just minus sine u. Okay, derivative of this, v is like a constant. So I'm sorry, u is like a constant. So that's a constant. So just cosine u. And then finally, sine u. Then we get to cross. All right, when we cross here to here, we get negative v sine squared u. And then when we do minus, then this right here. So minus v cosine squared u. Not too bad there, right? That's just going to become negative v, because we can factor negative v out of both of those. Middle one, negative v cosine u sine u. But then I have to change the sign of that, so it'll be v cosine u sine u. But then I'm supposed to subtract, but then add, but then subtract. So it's going to wind up being subtraction of this, which is going to be v sine u cosine u. And those are going to cancel completely, right? That's really nice. And then the last component is going to be minus v cosine squared u, and then minus v sine squared u. And that one's going to be nice also. So at the end of this, we get a pretty nice vector. Negative v, 0, negative v again. So really, really not a bad vector to be looking at here. And then we have to take the magnitude of that. So what's the magnitude of that vector? Yeah, so the magnitude of RU cross RV is the square root of, basically v squared plus v squared, which is going to be root 2v. Y'all tired yet? I'm getting tired. No trick question. Ready for the integral? Okay, on the surface S3, we're doing x ds, which turns out to be the double integral over d, where the domain is controlled by this, right? Okay, so I'll leave it like that for now. And then it's x. What was x for us? Unfortunately, x is 1 minus v sine u. And then we have to multiply that times the magnitude of the partials, right, crossed, which is going to be root 2v and then dA. One more step, and then we'll go to the computer. 0 to 2 pi, 0 to 1. I guess I could have pulled the root 2 out a long time ago. V, 1 minus v sine u. This order does matter, because, well, it doesn't matter, but I've already written the limits of integration. So inner integral is v, and the outer integral is u. There we go. That's the one I'll put into the computer. It's pretty brutal, huh? A lot of work. Square root of 2 times v. 1 minus sine of v sine of v times sine of u. dv du. Let me just check that. Root 2. Oh, wait, I'm missing a v, aren't I? I'm missing a v. Didn't change it much, but it did change. Okay, so it looks like that's turning out to be root 2 times pi. So the final answer to this was the first one, which we got 0, plus the second one, which was 3/2 pi, plus the last one, which was root 2 pi. So of course, just this. All right. Let's just take a look at what's next, okay? Oriented surfaces. This is a good point. This is a good place to stop. So the next thing we're going to talk about is what we've done so far is we've said, today basically has been, if we've got a surface that we can somehow come up with a parametric representation for it, then we can find the equation of the tangent plane to that surface at any point on the surface. We can find the surface area of that surface. And if somebody gives us a scalar function on that surface, we can find the integral over that surface, the integral of that scalar function over that surface, right? Which could be like mass or something like that. That's what we've done. Now what we're going to do is we're going to put our surface into a vector field. So you remember in the last class we did line integrals, and then later on we put those curves inside of a vector field, and we calculated the work done, right? Something like that. Now what we're going to do is we're going to put these surfaces in a vector field, and we're going to try and add up like the contribution of the vector field through the surface, which in physics is called flux. So we're going to be computing flux. So we're going to be changing gears quite a bit in the next part of this section because the vector fields now come into play. So I think it's a good point for us to kind of stop. This is where we transition from scalar functions to surfaces in vector fields. I know you want to go, and I would like to just call it a day, but was there not another? Just make sure. Example 2. Okay, yeah, we can do that. Do that later. I'd like to talk a little bit about the final, because the final is going to be coming up a week from Wednesday. So just so you can start planting some seeds in your mind, this is not the final, but this is the final will be very close to what this is, okay? I don't plan on deviating from this much. So the first problem that I asked on this final was for students to find the maximum and minimum values of a function of two variables with a single constraint. Anyone know what topic that is? Lagrange or Lagrange, yeah. Okay. Single constraint, function of two variables, which is nice because you could have function of three variables with a single constraint, or like one of the take-home exams, function of three variables with two constraints. But this is pretty basic, function of two variables, single constraint. Here was one where it was a double integral. So I gave them the double integral, like integral from here to here, here to here, here's the function. And I asked them to change the order of integration. So like in here it's dy dx, I asked them to change it dx dy, which means you have to have a good grasp of what the region looks like and rewriting it, switching the variables around. So that was the next one. So I actually put on here, the first problem took me 3 minutes to do. The second problem took me 3 minutes to do. The next problem was to find the volume of a solid region bounded by 4 different equations. So find the volume of a solid region bounded. What do you think that's going to require? What topic are we in here? Volume of a solid region bounded by all these different things. Triple integrals. So we're in triple integrals here. So in triple integrals, you could be in Cartesian, you could be in cylindrical, which is like polar, or you could be in spherical, right? So this problem took me 5 minutes to do. The next problem was to evaluate a line integral. So the line integral, like this. They were asked to evaluate, which is what? What integral is that? You should recognize that. That's your work integral, right? Where C is some curve, and I actually gave them the vector function of the curve, the R of t, and I gave them the vector field. So this is just to use the formula compute. Took me 3 minutes. The next one was to evaluate this again. Another one of these. But this time, I told them to use the fundamental theorem of line integrals. All I gave them was the vector field. Okay, so let's see if we can talk about this, because we do have a little bit of time. I asked my students to calculate this. I told them that this curve that they needed to integrate over went from a point to point. I gave them this point, I gave them this point. I asked them to evaluate that, and all I gave them was the field. So this was given, the endpoints of the curve were given, and I asked them to evaluate this. So what did they have to do? Find the what? Figure out if it's conservative, right? How would you determine if this vector field is conservative? By the way, this is a 3-dimensional vector field. It was in 3D. So how do you check to see if a vector field is conservative in 3-dimensional space? That would have been from last class. Curl 0, right? Curl 0. Curl 0 vector, if the curl is the 0 vector. Okay, and then once you are sure it's conservative, what do? You find we call it something, potential. You find the potential function, and then you evaluate the potential function at the 2 endpoints. The next problem, I asked them to do this again. Okay? And I gave them a vector field, and then I gave them the curve that I wanted them to integrate over on the next one was something that did this. It was the curve C went like this, this, and then this. I gave them that C, and I asked them to calculate that, and I gave them the vector field. And this was 2-dimensional. So how do you think they went about that? Well, how did I go about that? I'm not sure how they did it, but what's one way you could approach that? Green's theorem. Because you have a closed bounded region, right? Your curve encloses a region. And so you could use Green's theorem here. Now your orientation is backwards because you're going clockwise around that, but you could just change your answer at the end, negative. This one took me 6 minutes, sorry. The problem before this took me 4 minutes. The problem before that was 3 minutes. So far this problem took the longest. I don't know why it took the longest. Shouldn't have. Okay, next one. Find the surface area of something. So now we're actually talking about like today. All right. 4 minutes. Next one. Calculate the flux, which we haven't done. This problem took me 10 minutes. Next problem, calculate the work. Again, but we're using Stokes' theorem. So this is actually, we haven't talked about this yet. And then number 10, the last problem, oh yeah, and the one that one took me 6 minutes. The last problem that I gave them, 10th problem, was to calculate the flux again, which we haven't done. So, and that comes from the last section of the, pardon?
How long did that one take?
10 minutes. So, you know, if you put this together, 3, 6, 11, 14, 18, 22, 26, 36, 42, 52. This took me a little under an hour.
Sometimes by 6.
So, yeah, 42, I think, what it's, 42, is that what I said? No, 46, 52? 52 minutes. So, you're going to have how long? 3.5 hours. So, you know, you get about 3 to 4 times as much time as it took me.
Can you go over the times for each one again? Just real quick.
3, 5, 3, 4, 6, 4, 10, 6, 10. Now, if you've paid attention to what I just went through, it doesn't look like I asked them to do a surface integral, right? Like I asked for a surface area, but I didn't ask them for a surface integral. That doesn't mean that you won't get a surface integral. I may replace the surface area with a surface integral. You know, this gives you just some idea of what I asked. 10 problems, you know.
So the stuff on the final, like, you're not going to ask the stuff that we posted over for the midterm, right?
The final is just from the last test on. Yeah, I'm not going to go back. Now, Lagrange wasn't on the last exam, so that's why it's on this one. Yeah, so it's all of chapter 12 and 13 and a little bit of 11, 11.8, and that's it. So if that helps you, hopefully you can take that and maybe go into your book, pick some homework problems that look like what I just said. You can start, it'll give you at least a little bit of a heads up on that to get going on it, okay? All right, have a good day. We'll see you Wednesday. I'll have those mini exams graded.